Good evening. June 6, 2023. 6-6. Yesterday, or the previous talk was a bit of a recap and getting into some of the considerations, the discussions of what is the differential and how to describe the aspects of the fields and some fields, and about the topology and the function theory, and then how the topologies and how neighborhoods are described are continuous domains of being of particular interest in the continuous functions of the differential geometry and the perfect approximations that differential calculus affords. And then there was some consideration of this identity dimension as an application of a particular realm or a subfield in itself to help relate these notions of the sheaves of the topology and the symmetries as of about these things, and the submersions for the differential geometry and particular linearizations. That in this notion of the differential geometry, a lot of it is about the linearizations or just the organization of coordinates or transforms, what result that there are solutions that become fungible. There was a lot of talk of the sensible, fungible, attractable, about how that gets into a general descriptive course, which makes it possible to describe problem solving of problems or challenges, or the setups, the Ansätze of story problems, or any kind of posed problem in terms of what are related rates and the differential, and these sorts of things that then arrive at, for the algebraic geometry, how to arrive at a means of this descriptive differential dynamics, the dynamics in the differential and the dynamics in the descriptive and the definitive. So that's just been the way that it's been kind of carried on, and it was sort of a recap of that from readings from these books that have been just kind of collected, and they're just samples of a sorts from a broader library, of course, and just like anything else, when there's kind of a reckoning of things, there's sort of the sampling, the observation, the measurement of things. That is, as far as this scientific or statistical Ansätze or setup or problem goes, compared to a logical and mathematical Ansätze or problem or setup goes, it's is relevant to be able to extract information and place this notion of the descriptive and the differential and the dynamics together about any collection of what's available as reference or sources, vis-a-vis then what remains is basically what's left under the mortarboard, as it were. That is the sum total of what's available to start ab initio from the beginning, in terms of then being able to make from what's sensible to figure out how that's fungible, and then in terms of what makes it tractable, that it starts in a very descriptive manner, being able to relay in natural language the effect and the intent and the meaning of things, and then it gets into the symbolic and the more quantitative for the qualitative, of course, and then finally into methods, which then make for solving and for numbers and this and that, and in terms of then when various parameters of a system change over time according to how they're measured, that there ends up being the consideration of the real-time calculator, and as regards to what is a calculator, and then with regards to algorithms and so on that make it for the sensible and fungible and tractable to have data structures for algorithms in what's the engineering or design of computers or computer engineering, and that then for computer science, which is mathematics with respect to usually the binary and the discrete and the logical in the sense of the arithmetical logic unit of the system on a chip that has usually a general purpose central processing unit, or perhaps what has a digital signal processor with regards to something, for example, like a floating point unit, or in the graphic card world, a graphic processor unit. These kinds of things with their different resources, what make facilities, so that then in terms of computing and resources, they're basically just numerical resources. They make resources for computing, and then mathematically, that then there's often quite a tight bond between the models of machine arithmetic, like the unsigned integer, or the signed magnitude, or the two's complement. Usual organization of the integer is two's complement. For the arithmetic logic unit, which is what implements the usual operations of, say, the math library of the C runtime, as a usual example, in terms of the usual scalar integers, and what are called scalars also, the floating point values, in terms of their sign, mantissa, and exponent, in terms of various standards which reflect the organization, numbers, and forms in the computer. Where in the theory of mathematics, we have our numbers are kind of perfect, and integers, there's infinitely many of them, including models where there's an infinity. In fact, there's models that start with 0 and infinity and just fill in the middle, vis-a-vis that start at 0 and go to 1 and proceed. There's models of numbers that start with 0, 1, and infinity and build out from those in the sides, compared to, again, the usual natural numbers, the natural integers, which some wouldn't have also start at 0 instead of 1. The whole numbers are 1, 2, and so on, and that the natural numbers, including 0, is for a usual sort of assignment where, in something like axiomatic set theory and descriptive set theory for number theory, the ordinals, which reflect the same properties largely as the counting numbers, in large part, start with 0, as it reflects the empty set, and on to infinity, or omega, the inductive set with infinitely many elements, infinitely many. So anyways, that's kind of our symbolic numbers, and then our symbolic continuum is similar. It's infinitely divisible. There's no smallest real number. And then when we look to the machine integers, there's two things going on. And one is that it's possible to define what make rules for these axiomatics, making axiomatic symbolic descriptions and definitions of the symbolic values and the representations, basically in this language of the derivations and proofs, to treat numerical quantities quite this way, and only eventually to run out how they get crunched by machine integers, or floating point values, or interval arithmetic, or arbitrary or extended precision arithmetic on the machine. And with things, there's some algorithms that basically make it clear how a number can be stacked up and added up in the other resources of the machine, which besides the CPU or processing steps is RAM, or heap, or memory, or space. It's those defining basically resources in time and resources in space, the system on the chip. And then that's usually called the Harvard architecture, vis-a-vis the von Neumann architecture, and with respect to stacked machines and such, which mostly as models of computation in terms of their bounds and their resources are pretty well defined. For somebody who has background for something like computer engineering, which is the design of the electrical circuits and the system on chip, largely according to standards. Standards are what make it possible that everything works together. And then also largely courtesy electrical engineering's empirical, which makes for the very large scale integration, makes sure that the integrated circuits can be implemented at very large scale with regards to that, according to the process usually of their etchings in the silicon and doped silicon and similar kinds of applications that can make up the PNP or NPN transistors and transistor arrays, or gate arrays. That these are how computers work. And then that's all results zeros and ones down there on the lines, and according to a clock. And then at any given point in time, it's sampled at the clock, and it's systolic. It just kind of pumps, kind of like that the crystal is the heart of the circuit, and it pumps electrons, or electron holes as it were, current through the gates in the chip, which corresponding to the behavior of the logic, or what are the guides or signals on the chip. That is similar, that it goes through those as the systolic flow machine, through the flow graph. And that for things like memory and solid state memory and this and that those are kind of reflected in terms of they're constantly pumped full, and that as well they can hold a value on this transistor logic. This is very usual for the computer engineering. And then the computer science is the relation of that zeros and ones to true and false, and to a routine, including the procedural and routine, meaning that procedures are followed. And then there's the functional, is the other kind of programming model. There's the procedural, the functional, say. That when we talk about computer science and programming, is to implement a program, which is a linear progression, largely, of evaluations of conditions by expressions from what are the higher level languages, which are as close as possible to like a symbolic language of algebra, or these high level languages of the descriptive, down to what's machine code. So the integers and the rationals and the real numbers of our mathematics then have what are basically implementations of two sorts in the computer. One is the machine integer, and it's a fixed width, meaning that's the usual definition of the bits of a chip. An 8-bit or 16-bit or 32-bit or 64-bit chip has registers which fit upon them 8 or 16 or 32 or 64 bits, respectively, of the bit being the binary digit, and that each of these has a value of 0 or 1. And so a given 64-bit register, which is pretty usual size of the commodity peripherals these days. Like a usual phone will have a 32-bit chip, and a usual PC will have a 64-bit chip. That it can thusly hold on one value, and that this 64-bit value is also basically the unit of address in memory also. But the unit of address in memory is usually a byte, and it reflects 8 bits. But in terms of there's considerations of alignment, which reflects the modular, that the aligned values according to the register transfer logic of how these values come and go from the chips registers, and when the operations or mu ops or the pipeline ops or the the RTL, register transfer language, is implemented on the microcode on the chip. What happens is then, according to the number of these registers at a time and number of the cores of the chip, that basically each of the cores has its own registers, or with regards to then a task switching and this kind of thing, which kind of flash the entire contents of all of them at once on and off to a context, so that preemptive multi-threading enables multiple processes and procedures to kind of run at the same time by task switching. That the 64-bit value is an operand to various notions like add, div, mul, and subtract, and the arithmetic operations, and then as well the binary operations, and, or, XOR, and not, and complement. And so how it results is that then the instructions are only as many instructions as the entire subsystem on the chip, or the chip, has. the core has. And these are basically called their codes, their op codes, or what are the operations that make the codes. And then they reflect that according to these op codes, they'll just be organized that for any one of these given registers, there's usually 4, 8 or so working registers. And that these are organized by name, and also they're partitioned by the values, so you can treat a 64-bit register as a 32 or 16-bit register, an 8-bit register as a byte. Or sometimes for the what they call the multimedia or the parallel or vector instructions, you can treat a 64-bit register as 8-bit registers. In terms of that as operands, that it will be applied piecewise, pairwise to another operand, and so you can compute 8 at once. Right? And this should be pretty obvious, for example, for things like the binary operations and or XOR and NOT and complement, and that they basically are independent, bitwise, pairwise. And then for things like addition and subtraction or multiplication and division with what includes carry and overflow, then that's just implementing the chip how it divides that up and carries that down. And then something like the carry or the overflow bit, it express the conditions where the result of the operation doesn't fit on the register anymore. And so that's what the usual notion is of that our mathematics' numbers are closed under the operations. Now, it's not necessarily as tractable to keep track of larger numbers or the less significant bits of larger numbers. When you talk about 1,000,000, 2 cents doesn't really matter. But at the same time, it exists as it's an extended precision value. And then we could talk about also scientific numbers, which basically only have a certain digits precise. And so when you take the product of 2 scientific numbers, the one with the less digits precise is how many the result has precise, because what's beyond that is imprecise. So adding 1,000,000 and 2 cents, you'd only end up with 1,000,000. If the 1,000,000 was only precise to like 3 digits or so. And similarly, 3 or 4 significant digits is usually considered precise down to the thousands and 10,000ths, this kind of thing. So anyways, not the symbolic numbers, our logics, mathematics, algebras, the complete order fields, and non-standard natural integers as numbers, and not the scientific numbers, but these machine integers then have usual representations as either the first bit is the sign plus minus, or they're unsigned, and they only represent non-negative numbers. And otherwise for the sign numbers, they'll have what's called 2's complement, which is basically taking that the negative numbers are represented what would have been the higher order numbers, so you can just add them together and it ends up according to the same operation. You can add positive and negative numbers this way, and that the machine logic does that uncaringly. But then if you actually were to look at a negative number in terms of its bits, you need to convert it from a 2's complement representation to a sign magnitude representation, which is what the library does whenever it formats one of these numbers or prints it, shows the negative sign in front of it. That's how formatting a locale and stuff works on 2's complement. Then the other usual organization is called a floating point number, and so these are like often 80 or 120 bits wide. And what they do is they have a sign bit, and then certain amounts of the numbers are considered the mantissa or the digits that are the significand or what, and then and excuse me if any mistakes are my own. And then the exponent is the powers of it to the powers of 10, usually e10, e to the power 10, so that you can write numbers that are quite large in terms of having quite a few significant digits and quite a large or small exponent in terms of very, very large numbers or very, very small numbers, without having the entire extended precision of a big integer or big decimal with arbitrary precision, which is a higher level data structure than can fit on a register, but can be built in memory and be treated by algorithms and procedures and such as a higher level object, not a scalar anymore. That anyways, these floating points are scalars, and they're native on the registers of the chip, and according to the transfer logic, in and out of memory, and they have also a few reserved values, kind of like after addition or other arithmetic. There's carry or overflow, sometimes implemented. Then for the floating point numbers, there's also that. Then as well, there's a constant for not a number. So if you divide a floating point by 0, it may cause the procedure to crash, to exit unexpectedly, because it actually represents a fault. And what some architectures will trap that and fault and exit, and then other ones will just convert it to a value as not a number. Now in mathematics, we call that indeterminate quantities. So 0 over 0 is an indeterminate quantity. And something over 0, you could say either that's undefined, or you can say it's an indeterminate quantity. And similarly, infinity is not a number. So NaN for not a number is a usual constant, the value which is so for the floating point. Now, another thing about the floating point arithmetic is there's no necessary guarantee that for two given floating point numbers, you always get the same exact value. It will be within what's called epsilon, say, or there are certain intervals where it will be valid. So you might divide 1 by 3 and get something that looks like 0.333 and multiply it back and get something that looks like 0.9998 or something. And so you can't really test for the equality of floating point numbers, only whether or not they're less different than epsilon, which is another constant that's a floating point. It's basically an arbitrarily small value that, according to the size of the floating point registers, is arbitrarily small, and that the results of the closure of the arithmetic pairwise in operations, not necessarily all the way out the transitive, because there could be like cascading effects, and it depends on the implementation and design of the chip. But otherwise, at each step, you kind of have to check it and make it so. Then, if there's another kind of numbers that's very often found in computer organizations, are fixed point numbers. So if you're not necessarily using just what's called a general purpose CPU with its arithmetic logic unit that is bog standard, and its floating point unit, which meets standards like IEEE's floating point standards, then the fixed point is similar to the integers, except everything is behind a given radix. So it's like if you want to deal with decimal values to 2 decimal points, you could call it fixed point behind that. And if you're only going to deal with up to 4 or 5 or 6 digits or something like that, then you can fit that in 8 digits and then deal with that as kind of a higher level thing. So sometimes it's actually implemented in silicon on the actual as fast as it can go, because it's just in the gates and basically there's a functional unit called a piece of logic on the chip called an adder, that the adder is this kind of thing. Compared to some other standard logics like the roller and the shifter, making what's like a barrel shifter, and although that's kind of also related to things in the car, the barrel shifter or the roller shifter is when you get into 3D ICs, it's possible to implement a lot of things that come like that. This way, then the fixed point is kind of the complement of that. So it's kind of like the rationals, but it's just fixed point. So, and then there's not really notions of the rationals or the algebraics or the integers per se, but there's machine integers and there's floating point. So eventually, when you get to where it involves trying to compute numbers and crunch them out other things, then you also have certain symbolic constants, and then those constants like pi and e and other well-known constants are usually defined in the runtime. And then there's functions like sine and cosine and their inverses, and hyperbolic sine and cosine, and or cosh h and sin h and this kind of stuff. And sometimes a few other functions will be implemented in the runtime, i.e. on the chip, in particularly well-defined real-time execution times. And so then the idea is for these kinds of things is to figure out how to use these facilities as the resources of the chip. with regards to their scalar processing, their vector processing, and what results, how they can operate in the registers and keep stuff chained in the pipeline in the registers, or when there's register transfer logic, how it can be defined, how they kind of prefill or prefetch or otherwise proceed in a very linear way in their access to the memory, and their loading and unloading of registers with regards to the caches, which are located next to the registers basically, and are store an arbitrarily larger order of magnitude next to them. It's memory. And then there's this read and write through caches that go from that out to memory, and from that out to larger and slower memory, and that out from larger to slower memory or disk, and that out from larger to slower memory or the slower disk, and that out to the network, which is arbitrarily slow compared to anything that's on the disk, on the bus, or the chip via its caches. Arbitrarily slow. That compared to what's running on the chip, that what goes over the network is arbitrarily slow. That these days is still so fast that it is arbitrarily fast compared to what you can write on paper in finite time. So all that said, then there's lots of different things that go into numerical computing about that. Those are pretty much the limitations of what the numerical computing apparatus of the digital offers. It doesn't really have such notions as an analog computer. You can imagine a different system on a chip that implements a specific programmed gate array that does something like the transducer that Mogan describes as electromechanical effects and applications. In fact, one of those things, one of those transducers that Mogan describes as electromechanical effects and applications is one of the implementations today in one of these chips, as somebody's put it in silicon, makes up one of these what they call quantum computers, but what they really mean is analog computers. And things that can do stuff in real time at an arbitrarily high rate compared to what otherwise is this digital computers, analog computers. For the purposes, arbitrarily fast, and with arbitrarily high precision. Such an implementation is basically that Mogan's electromechanical effects and applications, the nonlinear, is used to describe how to implement an acoustic transducer on an entire layer of a chip, etching the whole thing, and then it just works from how it employs the whole. The disk, the blank, and then employs the entire etching blank and makes it on the chip. That's what just gets into what we call novel architecture designs on the chip. It's not so much quantum computing in this sense, because it's not really employing quantum effects to do that, except in the sense that the quantum effects are entirely well known and explained in terms of the nonlinear electromechanical effects and applications and this kinds of thing, which end up arriving how it drives it in what would be called custom logic. But that these days, the blanks of the chips that used to only be able to be connected via vias, that they had to be all planar, the entire flow of the systolic flow graph. There could be no crossings. It all had to go around and to be etched out in one thing and finally out to its contacts or traces. The idea was vias, so you could stack when the chips are being built and deposited and such, etched. And then there's that these days they can basically do that in 3D and just in arbitrarily many stacks, and the vias are small as this trace, and in fact you can have three-dimensional logic. So this basically makes that any kind of integrated circuit could be any kind of electrical circuit, and then besides that ends up getting into just plain old electron holes and electron circuit according to Ohm and Kirchhoff, and voltage and drop and capacitance. Largely capacitance is what all the gates are. They're capacitors, NPN transistors. That then something like the roller shifter implements both of the features of the roller and the shifter in one little piece, and then it's only a few layers thick, but it ends up being that it can take what would take an algorithm and it couldn't be done in real time, and instead can do it in real time. That as fast as bits come in, they come out. Because the idea is to have a chip, you want things to be real time, like a signal processor. compared to a procedural unit or functional unit. Because coming out of the signal processor for constant rate applications is that it comes out as fast as it comes in. That otherwise in chips, what you find in a lot of places in chips is you have buffers everywhere, and that the buffer is like, all I know is I'm going to have to load up all this stuff, like memory is a buffer in the architecture or something like that. And then finally when the unit, the working unit is ready, then it can start chewing away the buffer. So they call these buffers or queues or burst buffers. And so those being the facilities, the connections of the things on chip, then otherwise is the flow machine, and that is kind of how numerical computing can be implemented on the machine. And then above that is all the routines that go in to describe and define the algorithms that employ these resources, so that then they can reflect what are these the closed forms, which basically represent as an entire leap of things. That they basically represent that being able to compute the logarithm and use that for an estimate or an approximation or anything to do with statistical or sampling hypotheses or anything to do with methods of approximation or numerical methods, or anything to do with direct computation after a symbolic and closed form is arrived at, that it reflects for a particular configuration that's otherwise an unconstrained system, that according to configuration it's like, well, if it's unconstrained, if it's any possible thing, but when you make it a square, a lot of things become a lot simpler, like the diagonal is root 2 or something like that. It's computable. That then gets into as much as you can define that way up above, it gets into how it goes, that a system of zeros and ones is turned into a system of true and false, where the idea is that that's kind of what you call an arithmetization. When you convert a system that's a model, when you're talking about model theory, is like axiomatic set theory is just sets. What good is that? It's like, well, they're just arbitrary, arbitrarily stacked things. It's a stack of things. And then when you talk about making a model of that, you say, I can model a 64-bit machine integer if I have a set that can have 2 to the 64th many values, if a set of 2 to the 64 many sets, and that they implement this, especially if they implement how they hold together, they build a lattice out of 64 bits, and they hold an organization, this thing, and they do, and then you can call that a model. So the idea of descriptive set theory is only, what's the description of this thing is like, well, we're going to describe the set as like so, and then these other operations on some other sets, and then those obviously have to fit in one world of sets called pure set theory. They have arbitrarily tags on them that basically you make a method for means of differentiating, then making discernible these types of these things by tagging them. And then that within them, they have a way to remove the tags and then look at them just by the structure of that part of the model. So you got integers over here, you got functions over here, you got operands in integer arithmetic over here. They're each basically in a set of that kind, and then they have another value, kind of just like a pair of them or something like that. That as much as you get into the descriptive, it makes this universe of sets, or picking out of the universe of sets, which ones point to which models. And then that's all descriptive set theory is saying, it's a way of thinking of them as all zeros and ones, but it's the space of all the zeros and ones. And so we just start reserving the first few columns for the type, like code of what type of object it is, and then everything else after that is the values. And then as you get more and more of those, they get richer and richer, then there's more and more values of those, and you just fill it out. And there's results from set theory that says, oh, everything's definable and it's complete, so there's enough. And when you get to infinitely many, well, then it involves figuring out how to build up and build out those, and that gets into why there's the transfinite. because you can always take off, and besides that, you can always take off as many bits as you want. There's still infinitely many left. But also because that models that are big enough to encode anything you need to encode as a model, like the real numbers, are already big enough that they're found to exist in ordinary sets or extraordinary sets, where set theory is largely axiomatic set theory and it's well-founded, and that's its axiom, that it's well-founded. Everything else is just expansion comprehension, and everything's built on that up through the entire standard curriculum. So anyways, the idea is to figure out how to then relate what's this entire universe of pure set theory, because this pure set theory, all it sets is an arbitrary large universe of these sets, and then trying to attach anything to it that's really a true-false fact up here, that it's all zeros and ones down there and it's all true-false up here, that it's a universe of relation. Here the candidate set theory is being set theory because you only have to deal with one relation, and then you can also, it's figured that you can inspect things structurally by what they're elements of, and also what they contain. It's figured that it can be established which are which of those. That then they make a space of 0 and 1 bits, and then these are models of the things, right? So then when you get up to the higher level things, up in the library, the organization of thing, and you want to implement something like a calculator or a computer, then whatever goes into the descriptive differential dynamics here, for example, gets into definitions of integers and definitions of rationals and definitions of real numbers, definitions of functions, definitions of continuous functions, so on, dot, dot, dot. And then how I've been starting that is the toposes are spaces that are continuous spaces, they're continuous domains. And then there's functions like continuous functions. So topology and function theory are kind of first. And they build a geometry in the middle. And then there's algebra and then arithmetic. And it kind of rounds out, you see, objects in mathematics of geometry. Then with regards to the digital and sets and parts and zeros and ones and this kind of thing, then, and true and false, because it's all words up here. It's zeros and ones and true and false down there. In the pure, in the up here in the applied, it's only what's sensible, fungible, and tractable. It's sensible that we can put it into words. It's fungible in that we can relate it strongly according to a theory of models that we can prove they're types, where then the theory of types emerges, the theory of category emerges as definition and the descriptive above geometry or in the surrounds. That then there's for the model theory and this and that, then derivations follow. So after definitions, the derivations follow. And then the derivations of results follow. And then a model of that, the whole point of programming is to implement a model of that that's performant, that basically makes the best and most efficient use of the resources, which are bounded, meaning there's an infinite number of numbers in mathematics. There are an arbitrarily large but bounded number of computers to compute, including brains. But our brains are already kind of set up to deal with things in the higher level natural language already, and to make space for the certain and uncertain, as it were, your belief, desires, and motivations, these kinds of things, and resources. Humans are analog computers already, in a sense, and the apparatus can be kind of defined that way. So anyways, for this then setup of the symbolic, how it works out then, that these days the solutions are kind of defined and described to arrive at some various places when you're computing the differential equations solutions, that as you go along, there's a couple of different stopping points where it makes sense to farm the whole thing out to a solver, because it ends up being that, for example, well, you can reduce this to a system of linear equations and solve it, find its roots. And for example, there are libraries in the available as shared code in the computing, where they've already figured out how to model this domain and implement it according to the resources and the facilities in a very high performance implementation that makes use of constrained resources in a way that so follows, and as so far as that is formally defined in this, so that something like linear analysis, linear algebra, can be crunched because you just throw it to the linear algebra library. And similarly, something like, well, compute sine or cosine, from first principles is kind of tough, It kind of depends what the angle is, and then, via Pythagoras or what might be an approach, or these other ways to do it. It's built into the libraries, Addition and multiplication and division and subtraction are already defined, These kinds of things are already built in the model. Then there are higher level systems. Their computer algebra systems basically reflect this entire toolkit, grab bag toolkit of the mathematical setups that they, in their libraries, in their descriptive, have functions and routines and libraries that make models of these things, and so implement it this and that way. And this varies whether or not they kind of explain what they're doing, or the source code shows you what they're doing, or that statically you can analyze how they would do it, and this kind of thing. Vis-a-vis some kinds of algorithms that has gained a lot of employment these days is because this otherwise was all for deterministic algorithms and up to modeling error bounds and numerical methods. That for the stopping place, you can get off at linear algebra and it will give you solutions that are there within the precision. And then you can get out to numerical methods that will give you solutions that are up to their error terms or something like that. Then the idea is that for those being more the deterministic algorithms, then there's the indeterministic algorithms, and they kind of have a different playing field of their resources and their facilities, because they do not guarantee correctness. And you can look at something like just a floating point unit, that those can be faster because they don't necessarily have to be bitwise accurate or share the same results. And so this gets in a lot of things when there's algorithms trying to figure out something like, well, if you model this as a Markov chain, and so wanted to figure out how inorganic over time, the differential, you can arrive at kind of where it goes to in its limit. And then that's the Markov chain. And then, but this non-deterministic one that says, well, I can make about 1 billion different tries, and then if I see how it works out, I can Monte Carlo, which is kind of like throwing darts at a thing. Monte Carlo is a gambling house. You can go out, and the difference between a Markov chain is that it's ergodic, and it's defined by the supermartingale, and Monte Carlo is that it's stochastic, and it's defined by randomness. And so figuring to get in and out of minima and maxima by just trying many paths. Anyways, that's just an example, but in terms of otherwise the deterministic and the non-deterministic, is there different kinds of things, and the formality of what's guaranteed as a precision or lack thereof are different things. So anyways, the modern curriculum is pretty well defined and designed to get people up into differential calculus, and then the means of solutions to find the superposition of solutions, or to find the existence and uniqueness of solutions. It does make for them that there's a couple of places where it makes as much sense as ever to hand that over to numerical methods. Now this compared to the older school way is to resort to geometry and to figure that basically anything that you're going to relate to a model is you're also going to relate to a geometrical model and a model in continuous terms, and that then it's solved more symbolically. Now that there does end up, of course, still that there's methods like Newton-Raphson and approximations, and for example, the Fourier analysis and this and that we're talking about, or Newtons and Gregory's and Maclaurins and Taylors, all that went into using the finite differences and the vanishing differences to make for the Newton-Gregory finite differences and the Maclaurin and Taylor infinite differences to compute the Taylor series. And that then from, as just an example of a numerical method. So for Newton and Raphson and Newton and Coates and Gregory and Maclaurin and Taylor, these are good examples of numerical methods. And then these days you get into Runge-Kutta, and then there's other that these involve then. Once you arrive at a formulaic form for things, you can crunch it down and out if you can get it to a form that becomes tractable to one of these. Whether it's just computing the integral or the derivative, or computing the solutions to the integral and differential things, that's where numerical methods basically work Monte Carlo and iterative things in the stepwise for finite element analysis and this and that. And then they have their error terms and whether they're constrained or whether they blow up. So that is kind of just an explanation that today the computing apparatus for numerical computing is quite available. And so what I studied since last time, because I'm really mostly interested in getting back to the geometry and the algebraic geometry, because I already know how to program and I'm familiar with models of computation. And it still is better to do less of it. And so that gets back into what the subject was singularity theory. And the idea of there are a couple different names for the singularity, because it's basically where things cross and then or that they branch or bifurcate, or that's a catastrophe, or it's a perestroika, Russian for opening. It's a singularity. A singularity basically means a multiplicity. And so that a singularity is just kind of one way of looking at something, like the 3 squared and negative 3 squared are both 9. And 3 is the principal square root of 9. It's a singularity in a sense. So anytime there's more than one solution, or it's a multi-value function, you can think of it as having a singularity. And then when it's defined about how that branches, or somewhere it's called a bifurcation. And when it's otherwise, like if it goes from a linear to a disk, you can consider different various terms that reflect what is the domain it's coming from and what is the domain it's going to, between the principal and the alternates. It's a singularity in singularity theory. And so what I've been trying to figure out is, for the identity dimension, is just x equals y in 2 dimensions. And also considering this only in the positive, because then there's no consideration of the even and odd or the non-principal at all. It's just to start with, it's only in the positive numbers, non-negative numbers. And then as going up higher in dimensions, then it's x equals y equals z, or z, x, e1 equals e2 equals e3 equals e4 dot dot dot. Otherwise the coordinates in what reflects for the Cartesian, for the orthogonal, for that each of these coordinates has the same metric as if it was translated one to the other, that the values are the same, and this and that kind of thing. Gets into how then that this the identity function is a singularity in the middle, and one thing that interests me about it. So I went to studying the Taylor series, or here it's the Maclaurin series for 0. But the idea is that it's the 0th and first and second higher order dot 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 derivative times the value minus the where it's evaluated for and over n factorial. And the sum of those terms is called the Taylor series. And it's kind of built up after Maclaurin, Maclaurin wrote this great book in his time, and it's called The Theory of Infinitesimals, or The Theory and Practice of Infinitesimals. It's still good reading today. Maclaurin's book is the best old book that sounds most like modern English I've ever read. Maybe it was a translation of sorts, but I think it was just that was good. So anyways, for something like the identity function, after the first term, all the coefficients are zero, because its second derivative is zero, and while it's infinitely differentiable, all its higher order derivatives are also zero. And so that reflects a simple thing to help explain why, for example, there's a linearization for it, and then what it means for that outside the linearization would be a basis for why it's a singularity to add in and about and around it. And so what I've been looking at is an object in geometry called the regulus. And the idea of a regulus is that if you can, for any given surface, if it can be drawn as only straight lines, it's a regulus. As if you can patch out its shape and complete and fill out its shape, only drawing straight lines, a 3D surface. And so the only example, because I was looking for the example for the hyperboloid, because what I'm interested in is x equals 1 over y, or y equals 1 over x, because you got the identity and the inverse. And the inverse chart is the hyperboloid. And when I want that for xyz, I want that to be, xyz equals 1. That 1 over xy equals 1 is 1 over x or 1 over y. That parametrically, it's 1 over xyz ... equals 1. Well, the problem is that it doesn't really have, it's not really continuous in that sense. I only want the principal part of that to be what are the constraints where that they all fit within, they all have, they don't have any value greater than 1. So that's what I'm looking at, is that in terms of singularities and how that's going to be. Because then what I want to do is figure out, A, how that behaves in the infinite dimensional case, and B, I want to figure out how this, what kind of regulus or all straight lines draws that. Because if you take the hyperbola and just spin it around, rotate it around as rotating around the origin, you can draw that 3D surface with only a collection of all straight lines. And so I'm trying that when I was reading about that the other day, that's what I thought would be kind of one thing I'd want to find to help understand, to make how that then there's going to be built these complementary orthogonal functions about that in this space, about this identity dimension that's going to kind of fold out and fold down what then goes for these other things that are projected in and onto that space by these dimensions, that where it's singular in the middle, that it becomes instead an analytical basis about the meromorphic and getting around those things. Again, any mistakes are my own, but meromorphic, but generally applies to being able to complete analysis when other ends up against the coordinates, like an asymptote. It's like, oh, it's a singularity like an asymptote. Well, that's not the only issue here. And there's some way to get around that. You can, translate it over, solve it as symmetrical about the origin, and translate it back. Or otherwise to get that figured out in terms of these kinds of models. Make sure that these various models have ways to do this in terms of then the pairwise, especially in terms of two things, together and among each other as they interact. And then also for the all-wise, and the potential and this and that. The multi-body system. The whole goal is to figure out how to solve generally these multi-body systems of forces proportional to quantities and their inverses. Well, so that's going on. So let's see there. That was a brief description of modern commodity processing resources for numerical computing in the systems of chips and about buses and computers and their communications and connections and their form factors a little bit, but their descriptions in terms of their systolic and rates and these kinds of things, and about how it relates to the descriptive differential dynamics. A brief description of what it means to make a model of something from the universe of pure sets, to implement it as an arithmetization, or which is what you usually do when you just want to compute it for like some formulas or something, or as an algebraization, or as a geometrization. You just convert it to a model of that and then solve it in one of those. Here there was a description of what that means to make something that's symbolic from this universe of sets, build a model for it. So that's where we build our foundations and our rigorous formalisms, and then print that as a model given the facilities or the resources on the chip, and where that lets out, because the extended precision is unbounded, and floating points are bounded, and these kinds of things. That I'll carry on some more later as we get back to notions of the infinite series, according to basically that's going to reflect what's going on in the power series, and then that's going to and with respect to stuff like Markov chains and Monte Carlo, those being two kind of like the tracks of the deterministic and non-deterministic in the time series. And then that's going to be kind of built up as about around the operator calculus, in terms of the operator calculus is going to operate on anything in these series according to the ordinal index out to the non-standard, or x infinity, or when t equals infinity. And these are the kinds of things that go into total field theory, where a large body of the work on singularities, about the exotic singularities, is from relativity theory and physics, and the singularity theory of as I've been reading from Ehrman and Wald and Girac, and that these describe for various kinds of geometries and things. The coordinates are about like Chandrasekhar and Schwarzschild, the black hole, where we have white holes and black holes everywhere, sort of thing, and that these represent all these singularities of matter and this kind of stuff in the physics. That's kind of what a total field theory is about, is also that. And Kruskal and Chakris, and Rindler, but for Kerr, and the cube wall, and this was mentioned. Well, all right then. Hey, have a great day.